Hi, welcome back to part 2, acceleration and velocity. Now I did make a mistake on part 1 when I originally drew my acceleration graph. I actually called that the position graph right there. I saw that the path. But this is really our acceleration because remember we're looking for the tangential and the normal part of acceleration. So make sure you fix that. I did kind of have it down here correctly and example down here. I did mess up here, so please make sure you fix that. So let's go ahead and take a look. We're going to take a look at some examples from calculus. Cal 1 and Cal 2 it should look a little familiar to us. We're given the acceleration vector. Now notice this has a 0I component to it. We'll talk about that. And given the particle starts at the following location, 1, 2, 0, and the particle starts from rest. So this is basically giving us our initial position, and this is giving us our initial velocity. We want to find the location of the particle at t equals 2. So we know we're going to need our position function. Going from acceleration, we should remember from calculus last year that we go to velocity. We have to take the antiderivative to get velocity, and from there we take the antiderivative to get position. So this is going to be kind of a lengthy problem, so hold on to your butts because this is going to get lengthy for us. Alright, so first of all we have to find velocity. Alright, so to do that, we know we have to take the antiderivative of acceleration. Now, there is no I component here, so I'm going to add an I component. This does become important for us later on if we get out of that habit. So to get the velocity, we are going to integrate we're going to integrate our I component first. So that becomes 0I dt plus j dt plus 2k dt. The integral 2k dt. No, I like to do each one separately. You can do all this in one single chevron. That's okay too. I've always liked to separate them out. That's just how I roll. It's funny, your last week rolls. Okay, so when I integrate, of course, here, for the first one, our velocity, we would get 0t plus c1 I plus, this becomes t plus c2j plus, over here, 2t plus c3k. And now we're going to use our initial position, initial velocity, to give us c1, c2, c3. Now our initial velocity is at rest, which means all of those components have to be 0. So if I set each one of these equal to 0, so for my I component, we could get 0 equals, that's just 0 plus c1, so c1 is 0. Go for the j's, we would get 0 equals, that just becomes 0 plus c2, so c2 is 0. It's a lot of fun when everything's zeros, except for your homeworks. Here we get 0 equals 2 times 0 plus c3, c3 is 0. And that gives us our initial velocity, our velocity function, which will become 0I plus tj plus 2t, whoops, that's weird looking t, k. And there is our velocity function. Now, even though that's 0I, you don't need to put the I here because it's 0, but when we start finding the position, that I component will have an impact on us. So I like to have it just because of that. So finding the initial position now, I am going to integrate velocity. So this becomes 0I again, don't forget your differential dt, plus, over here we're going to get the integral of t dtj plus 2t, don't forget your differential, dt, k. Now, should you put the dt or the k first? Of course, the dt. The k is just my directional component, is my directional component there. Alright, so when we integrate now, we're going to get, here we're going to get 0t plus c1 I plus integral of t squared is, of t is just t squared over 2 plus c2j plus, and 2t becomes t squared plus c3 Okay. And now we have to find the components. So this is what they're telling us. R of 0, the initial position, is 1, 2, 0. So what that's telling me for the first one is if my I component is now 1. That's my I component. So we got 1 equals 0, because my t is 0, plus C1. So C1 is 1. Go over here. This is my J component is now 2. So this becomes 2 equals 0 plus C2. So C2 is 2. And my K component is 0. So I get 0 equals, at T equals 0, plus C3. So C3 is 0. So our position vector, R of T, is being given as I, 1I, plus T squared over 2 plus 2 J plus, kind of ran out of room here, T squared K. Now we're not done. R of 2 therefore would be the following. Plug in 2, well that's just going to become 1. 2 squared over 2 is 4 over 2 is 2, plus 2 is 4, and I get a 4 here as well, T squared. Alright, and there is our position. Told you, that's a long problem. I mean, that is just lengthy. I think my hand hurts after that one. Alright, question B. If the acceleration vector is given by this, so again, they're giving me the acceleration vector, find the object's velocity and position functions given the initial velocity vector is, well, this is kind of the same thing. V naught is, now again, there's no I component, so they're telling me it's 0, 1, negative 1, and my initial position, R naught, or not, 1, negative 2, 3. And we are definitely going to be integrating here. So to get velocity, now hopefully we've been integrating long enough, we can kind of do this quickly in our head. This just becomes T plus C1 I plus 2T plus C2 J plus, and this becomes 3T squared, be careful, 3T squared plus C3 K. I just integrated. Remember, velocity is the antiderivative of acceleration. Don't forget your differential. I just did that. I just did all the math work in my head. Using my initial velocity now, I can solve. So we know that V naught is 0, 1, negative 1. I can just plug all those in. So I would get 0 equals 0 plus C1. So C1 is 0. 1, so I get 1 equals 2 times 0 plus C2, so C2 is 1. And then for C3, we know that's negative 1 equals 3 times 0 plus C3. C3 is negative 1. So my velocity function would be, I guess I should write this in, I'll write this in component form, Ti plus, this becomes 2t plus 1j plus 3t squared minus 1k. And again, you can write this in component form, or chevron form if you like. And there is our velocity function right there. Alright, to go get our position function, we do the same thing, but now I'm going to integrate again. So let's see, r of t, remember, is the antiderivative of v of t, dt. So let's go ahead and calculate this. I'm going to run out of room here, so I'm going to write down here. This becomes t squared over 2 plus c1 I plus t squared plus t plus c2 j plus t cubed minus t plus c3 k. Oh, ran out of room there. Oh. I'll pause here for a second. Make sure you get caught up there. And then we know that the initial position is going to be 1, negative 2, 3, and I can just plug all of those in. For my I component at 0, if I let t be 0, I get 1 equals, that just becomes 0 plus c1, so c1 is 1. My j component, again, t is 0, so I'm going to get negative 2 now equals 0 plus c2, so this c2 is negative 2. My k component, well, my k component is going to equal 3 when t is 0, so I get 0 minus 0 plus c3, so c3 is 3. And then I can write out my position vector. And I'm going to write this in chevron form. Why not? So this is now going to become t squared over 2 plus 1, and that's in my I, t squared plus t minus 2 in my j, and I get t cubed minus t plus 3 in the k direction. And there is our position vector. All right, go to part 3. We'll take a look at the very last example. I'll see you then. Bye-bye.